All right, welcome back to Calculus. Today we're going to get ourselves started on section 3. And what we're going to continue to do is find volumes of solid three-dimensional shapes using the process of rotation. So far what we've done is we've looked at finding volumes using disks. So creating a three-dimensional shape, then slicing it. And in some cases, the slice turns out to be what's called a disk, which is just shorthand for a real short cylinder. And what we're doing then is stacking up an infinite number of these disks. So we'd have one disk on top of another, and we're adding up an infinite number of disks. All right, and our formula for finding every one of those individual disks was pi times the radius squared times h. And it was really, really important to understand in what direction h is, whether it's vertical or horizontal, because that then tells you what variable we're supposed to be working in terms of. Then we moved on to a shape called washers, and again, creating a three-dimensional solid by rotation, and then slicing it. And this time, in this case, the shapes that we get are called washers because they have this hole in the middle of all of them. And so the formula then became pi times big R squared minus little r squared times h. We find the volume of the big disk, and then we subtract away the part in the middle that we remove. Okay, those are the two methods that we've got so far. Well, starting today, we're going to look at a third method called shells. And what we do with shells is we think of any three-dimensional solid, so please consider the cylinder that I've drawn off to the left. A cylinder, of course, has just got a circular top, and then it's got a height to it. So we'd have a radius here, and we'd have a height here. And what we're going to do is we're going to think of it as a roll of paper towels. I was going to think of it as a roll of toilet paper, but you just can't find any in the grocery stores anymore. So let's go with paper towels instead. And what we're going to do is we're going to think about peeling a layer of paper towels off. So we're going to make a cut down the side as I've tried to do in black there. I'll go over it again in red. And then we're just going to peel off a layer, a complete layer of paper towels. Now when we lay it flat, when we lay out that layer flat, what we get is essentially a rectangular prism, a box. All right? And to calculate the volume, we just simply multiply the length of the box by the width of the box by the height of the box. All right? And then what we're going to be working on is how to express the length, width, and height in terms of variables on a coordinate system. So either in terms of x's or in terms of y's. Now, the length of the layer is actually going to become or is equivalent to, I should say, the circumference of the circle. If you think about wrapping that layer back around the cylinder, that wrap, when we unroll it, becomes the length of the cylinder. Therefore, the length is actually going to be 2 pi times the radius. So the length is going to become 2 pi times r. Now the width is going to either be a vertical or a horizontal direction. In this case, my very first picture I've drawn here, it's a vertical direction. So we're going to have to think in terms of how to calculate that vertical direction. Okay? And finally, the h, the height, is always going to become the differential. Because we're going to be doing this an infinite number of times, h gets infinitely small, so that becomes the differential, which is either going to be dx or dy. Okay? And of course, we're not going to do this with just one layer of paper towels. We'll do it over and over and over and over again. So go from the outside of the roll of paper towels all the way to the inside. Or vice versa, we could start on the inside of the roll of paper towels and work ourselves to the outside. Okay? Now, you guys are going to need two formulas to work volumes by shells problems. Okay, and what I've done is I've taken a small roll of paper towels that I still have left in the classroom, and I set it on your desk either vertically or I laid it down, so horizontally. Now, if it's set vertically on one of your desks, let me choose red here, you'd have to pretend that the y-axis is going through the middle of the roll of paper towels, and therefore the rotation would have been done about the y-axis. When that's the case, when we're rotating about the y-axis, what we're going to have then is a length to every one of the layers, a width to every one of the layers, and then what's really hard to draw, but I'll do the best I can, is an infinitely skinny height to all of the layers. And as you guys look at that layer of paper towels coming off the roll, would that layer be infinitely skinny left and right, side to side, or would it be infinitely skinny up and down, vertically, top to bottom? And the way they're coming off, it's side to side, therefore our differential is going to become dx. And so the formula that we're going to be working with is 2 pi x. That's going to get us the circumference of every layer, which is equivalent to the length of every roll. F of x is going to be equivalent to the width, and then the dx is going to be the height of every one of our layers. Okay? Now the other option is for us to do the rotation about the x-axis. So what I need you guys to do is pretend that the x-axis is going through the middle of the roll of paper towels. And again, the important thing is we're going to have a length going this way. We'd have a width going this way. But again, the tough one is the height. All right, as these layers come off, please notice that the heights are going to be infinitely skinny. That's going to become our differential. Infinitely skinny up and down, vertically. Therefore, that height is going to become the differential dy, which you can see in my formula. And therefore, if the differential is dy, the width has to be in terms of y, and the length has to be in terms of y. Remembering, all of these variables always have to match up. Back here, all of the x's had to match up. All of the y's have to match up. Okay? So in any problem, what we're going to do is pretend that we're creating a strange, weird roll of paper towels. And we're going to peel off layer after layer after layer after layer and add all of them up. And of course, when we add up an infinite number of things, we're going to be integrating. Okay? Alrighty, so let's give 2 of them a try and see how we can do. Like we did with both discs and washers, we're going to start with a series of equations which would give us a 2-dimensional region. So I'll start you guys off here with the straight line y equals x minus 1. So that's going to be a straight line that hits the y-axis at -1 and has a slope of +1. So it would look roughly something like that. Y is equal to x minus 1. X equals 4 is a vertical line that goes through 4. So 1, 2, 3. I'll put in the 3 there for everybody. So a vertical line through 4. And then y equals 0 is hard to draw because that's a horizontal line through 0. So kind of a tough one to draw because it's essentially on the x-axis. So the 2-dimensional region then is going to be this triangle right here. Okay? So just like discs and washers, start with the 2-dimensional region. Now do the rotation. You can see at the end of my problem, the rotation is around the y-axis. So we're going to take that 2-dimensional shape and rotate it around the y-axis. To help myself out, I'm going to draw a mirror image of the triangle on the other side so I can kind of get a feel. So when I try to make the rotation, I can try to draw at least a decent picture. Let's see how I can do here. All right, so we're going to have a little circle there. We'll have a circle there. And then let's say we can see the whole top of this fella. Okay, and the axis of rotation, the y-axis, would be right through the middle of that shape. So as we've done before, we get kind of a weird looking funnel shape. And we're going to try and calculate the volume. Okay? Only this time we're going to try to calculate the volume using shells. Okay? We're going to pretend to peel off layer after layer after layer of paper towels. Okay? And we're going to be adding them all up. Okay? So if you think about the innermost layer of paper towels, I'm sorry, before I even get started with that, please notice that since the rotation is going to be about the y-axis, look back at your formula, please. Because the rotation is around the y-axis, everything has to be in terms of x's. Everything has to be in terms of x's. So now let's go to the x-axis. Where would the innermost layer of paper towels be? It'd be just a really crazy skinny layer, but the innermost layer of paper towels would be at 1, and then we'd go out, 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 and then the outermost layer would be at 4. So what we're going to be doing then is integrating from 1 to 4. Okay? Those, please notice, are off the x-axis. Okay? Then what we've got is the circumference, so 2 pi times x. Then, so this, let me change colors so you guys can clearly see this. So this will be the length of every one of the layers. Now we need the width of every one of the layers. And the width of every one of the layers needs to be in terms of x. All right? And please notice that the widths change. When we're close to 1, the widths are pretty darn short, but the further we get out, the widths of the layers get taller and taller and taller until the very outermost layer would be 4 tall. So how are we expected to find that value? We need to make sure that fella's in terms of x. So how do we find that value? Well, we actually have a function. Let me choose my laser pointer here. We have a function that gives us that width. Notice it says y equals, because all of these are vertical measures. All of these are vertical measures, so we see something that says y equals. Vertical measure, y equals what? X minus 1. So we can replace the width with x minus 1. And then finally, the height of every one of the layers, because we're going around the y-axis, is going to be the differential dx. And there's the complete setup then for our integration. Okay? We have the limits of integration off the x-axis. The radius of every layer is on the x-axis. The width is in terms of x, and the height is the differential dx. Okay? So the important part, when you guys start doing these for your assignment, when you do these on your test, probably about 60% of the value of the problem is going to be in the setup, all right, what I've just written down. The rest of it is going to be that will then be the integration, which here, what I'm going to do is factor out the 2 pi. It's just a constant, so just get it out of your way. And then distribute the x inside the parentheses. And then I just have to give us a little bit of room to work here. And now we can integrate. So what we'll do is add 1, divide by the new, add 1, divide by the new, and then we'll be f-taken from 4 down to 1. So I'm going to leave the 2 pi out front, just multiply at the end by that. Now everywhere I see an x, put in 4, so 4 to the third over 3 minus 4 squared, excuse me. Oh, I screwed up something there. What did I screw up, guys? Oh, I have a typo there. Sorry, let's go back. When I integrated, the integral of x squared is add 1, divide by the new. The integral of x should have been add 1, divide by the new. So my error is I should have had a 2 in the denominator. Sorry about that. So then now put in a 4 to the third over 3 minus 4 squared over 2. There we go. Minus, now put in a 1 to the third over 3 minus 1 to the second over 2. Okay, and now let's just dig out our calculators and punch out the math on this fella. Okay, so here we go. 64 thirds minus 16 halves, I believe it is 40 thirds. I could double check myself. 1 third minus a half is negative 1/6. These two negatives make for 1 plus. So 40 thirds plus 1/6 would be 81/6. 81/6. And then when I simplify, do a little canceling and multiply by 2, what I should get, if I punched OK, is 27 pi cubic units. So the volume of that solid, 27 pi cubic units. And as before, feel free to leave your answer as an exact value, 27 pi. If you prefer, you could punch that out as a decimal as well. Totally up to you. Okay, and let me shrink this up so you guys can see it on one page if that helps. All right, so that would be our first example. Again, please notice rotation was around the y-axis, so everything was in terms of x's. Okay, now let's go ahead and slide across and try one problem where the rotation is around the x-axis. Okay, again, we get ourselves started by drawing a picture. And again, I know this first equation might be trouble because you can't use your calculator for that very well. But this would be a parabola that starts at 4 and with the negative opens to the left. So it'd be a parabola that opens to the left. Okay? Then use x equals 0. So that's just going to be a vertical line through 0. So it's kind of hard to see because it's the same as the y-axis. And then my problem says just look in quadrant number 1. Okay, so if we just look in quadrant 1, that would be the two-dimensional region. Now the rotation is around the x-axis, so we're going to rotate that around the x. It's kind of nice because we already have the mirror image down below. And so the solid then, when I try to make this look three-dimensional, just do the best I can. Would look something like that. Okay? Now, it's going to help us out in just a little bit. If before I get going too far on anything else, I'm going to need, sorry guys, my screen's acting goofy there. Before I go any further, it's going to be helpful to figure out where this curve hits the y-axis. And it can either be below or above. I'm going to choose to go above. But where would that cross the, excuse me, the y-axis? And that's going to be at 2. And if you don't believe me, all you'd have to do is take the equation for the parabola and replace x with 0. And when you replace x with 0 and solve for y, you'll get y equals plus or minus 2. And it really doesn't matter if you choose the negative 2 below or the positive 2 above. It doesn't really matter. I'm going to stick with positive numbers though. Okay, so to calculate the volume of this solid then, we're going to integrate. We're going to integrate. Okay, so we're going to be integrating. Again, we have to think of this as a roll of paper towels. So we have to think about where the inside would be. Okay, the inside is going to be the x-axis. Okay, and so where are we going to be integrating from? The innermost layer of paper towels is going to be located at 0, and the outermost layer would be located at 2. Now, if anybody would like to, another option would be to integrate from negative 2, let me use my laser pointer, would be to integrate from negative 2 up to 0. Okay? So if you replace 0 with negative 2 and positive 2 with 0, we'll get exactly the same answer. Totally up to you. Okay? Just a repeat, because we're rotating this around the x-axis, everything has to be in terms of y. So here we go. So the length of every one of my layers of paper towels then is going to be 2 pi times y. Then the width of every one of the layers, of paper towels. Now please notice the widths are going to be now horizontal. And do we have something that reads as horizontal? Sure, right here, because it says x equals. X equals is horizontal. And luckily for us, that's in terms of y, so good for us. So the width is then going to be 4 minus y squared. And then finally, the height of every one of the layers, when we're rotating around the x-axis, that's going to be the differential dy. And that then would be the complete setup for the volume. Okay? So feel free to pause the video if you need to take a look or examine your formulas, anything like that, to see how we set that up. But now I'll just move on to the computation. I'll factor out the 2 pi, get that out of everybody's way, and then distribute the y inside. So y times 4, y times negative y squared. Slide the screen up so we have a little bit of room to work. And now integrate. see if I can do it correctly this time. Add 1 to the variable, divide by the new. Add 1 to the variable, divide by the new. And this time we'll be f-ticking from 2 down to 0. A little bit of simplifying before I f-tick though. The 4 and the 2 would cancel, leaving me with the 2. And so now my f-tick, again just factoring the 2 pi out front just to get it out of your way. Now everywhere you see a y, put in 2, so we'll have 2 times 2 squared minus 2 to the 4th over 4 minus, everywhere you see a y, put in 0, so 2 times 0 squared minus 0 to the 4th over 4. All right? So let's see, 2 times 2 squared is 8. 2 to the 4th divided by 4 is 4. 2 times 0 squared is 0. 0 to the 4th over 4 is 0. So obviously we have 8 minus 4 and 0. So 4 minus 0 is 4, and 2 pi times 4 is 8 pi cubic units. And so our volume then, guys, for this solid, again, try and get it all on one page here so you can see the whole shebang. The volume for that solid form then is going to be 8 pi cubic units. Okay? Now, that's all of the new material from section 3. I'm going to have at least one more video, though, that you can choose to watch. That's just going to give you more examples of finding volumes by a method called shells. Okay? So feel free to watch any of the other videos in this lesson, but you've seen all of the new material that's required. Okay? So hope you're having a good day. Talk to you soon.